As you might be aware, positive feedback will be often employed in the case of oscillators or signal generators that will convert the DC energy into varying energy or AC energy, so that the output of an oscillator can be a square wave, a sawtooth wave, or a triangular wave, or a sinusoidal oscillation. We will now see a very classical oscillator, that is Wien bridge oscillator, being constructed using Opamp. You can construct Wien bridge oscillator using transistors also. The role of the transistor is to provide the necessary amplification so that the criteria for sustainable oscillation, that is the Barkhausen criteria for sustainable oscillation, is satisfied. The modulus of gain of the amplifier in the oscillator circuit and the feedback to the amplifier must be equal to 1. And for such a configuration, the output will be infinity, or the output will be large comparing with the input, and the gain will be tending to infinity. And for providing such an infinite gain, you require to have a positive feedback. So that is the purpose of positive feedback. And this is called a bridge oscillator because this is functioning under the assumption that it acts as a balanced bridge. The amps of the bridge are this resistance R1 is a branch, RF is another branch. Say this tank circuit C1 R1 is one branch, and this feedback path C2 R2 series tank circuit or series resonant circuit, not a tank circuit, series resonant circuit is another branch. And we already know that in the case of Opamp there is no current flowing through this path, so this is always a balanced bridge. However, there will be some conditions that are to be satisfied for the balancing of the bridge. So the bridge can be shown like this. You have this Opamp here that will be functioning as a current carrier, and you have a resistance, one branch here, that is this resistance, say R1, and this is connected to ground. So this is your ground terminal. Another branch, say RF here, that is connected to a voltage point VO, that is output voltage point. So this is RF. This is being connected to the inverting terminal. And at the non-inverting terminal you have another branch. The end of this branch is also connected to the ground terminal. Here it will be consisting of a parallel resonance circuit or a tank circuit having components resistance R1 and capacitance C1. And this is connected to this terminal. And here you have a series resonance circuit consisting of resistance R2 and capacitance C2. So this is the balanced bridge. Now current is assumed to be, say, flowing through this path so that the bridge is balanced. There will be a definite ratio of resistance between R1 and RF, and the impedance between this branch and this branch. Let this has an impedance Z1 and this has an impedance, say, Z2. So this is always a balanced bridge, and it will produce oscillation here. How this oscillation arises and the working of the circuit, we will now look into it. So this is about the configuration. The Opamp is in non-inverting configuration actually, and it has a positive feedback also. A part of the output energy appearing across this impedance Z2 is injected to the non-inverting terminal, so it's a positive feedback. And to the non-inverting terminal, already this capacitance resistance parallel resonance circuit will be producing a sinusoidal oscillation that is being given. So already a signal is given to the non-inverting terminal. However, this is an RC tank circuit. It will be associated with the heat loss of energy, so that the sinusoidal oscillation produced here will be some kind of damped oscillations. To make it a regenerating oscillation, the loss of energy on the course of each and every cycle must be supplied back to it in phase with this signal. To have this in phase feedback, we employ a positive feedback, and a part of this output energy is injected with this damped oscillator, so that sustainable oscillation can be obtained here. So now we will see the working under two different titles. Role of the tank circuit. Once the circuit is switched on, the output may be switching into plus V saturation or minus V saturation. Let me take it say plus V saturation. That will cause the capacitor C1 in the parallel tank circuit to charge. As it receives a large charge, it will be discharging through this resistance, say R1, and this cycle of charging and discharging continues once the capacitor is given a charge. This will cause a sinusoidal oscillation whose amplitude will be falling on the course of each and every oscillation. That's a damped sinusoidal wave is produced here. This signal is being given to the non-inverting terminal. So the role of this op-amp is to act as a non-inverting amplifier. This will amplify the damped sinusoidal signal with a gain of 1 plus Rf by R1, and an output will be produced, and an amplified output will be produced. On the course of this will be producing continuously oscillations, however, the amplitude of which will be going on falling. To supply back the loss of energy, a part of this output energy is taken using this impedance divider consisting of impedances Z1 and Z2. The part of output voltage VO appearing across Z2 is injected back to the non-inverting terminal. That undergo an addition with the signal already coming from the tank circuit, so that we will be getting sustainable oscillation in the output. So the role of the amplifier is to act as a non-inverting amplifier having gain 1 plus Rf by R1. Role of this parallel tank circuit is to produce the sinusoidal oscillation. And what will be the role of this series resonance circuit? If this circuit has a natural frequency exactly same as that of this one, then this will be capable of injecting back part of the output voltage in the same synchronization as that of this tank circuit. That is why this circuit will be capable of providing energy to that waveform produced by the tank circuit in such a way that the loss of energy in each cycle will be supplied back. So for the proper working of this circuit, we require the resonant frequency of this parallel tank circuit to be exactly equal to the resonant frequency of the series resonant circuit. So always that assumption is there. That means R1C1 time constant will be equal to R2C2 time constant. That means in a special case often we take R1 equal to R2 and C1 equal to C2. So C1 equal to C2. Now let's make a qualitative analysis. For sustainable oscillation being obtained, the Barkhausen criteria must be satisfied. That is A beta equal to 1. Gain of the amplifier is A equal to 1 plus Rf by R1, and beta that's equal to Z2 by Z1 plus Z2. We will now evaluate Z2 and Z1 and substitute here. Z2 is the effective of this parallel combination. Z1 is the effective of this series combination. In parallel combination, if there are two resistances R1 and R2, effective is R1 R2 by R1 plus R2, product divided by sum. So Z2 is R1 into 1 by j omega C1 divided by R1 plus 1 by j omega C1 divided by Z1 plus Z2. Z2 is this term itself. I have repeated it here. Z1 is R2 plus 1 by j omega C2. And of course, we have this modification R1 equal to R2 equal to R, C1 equal to C2 equal to C. So all these subscripts are being eliminated. Now, R by j omega C into cross multiply this and multiply with the numerator with the reciprocal of this cross multiplied product. That is now 1 plus j omega RC divided by j omega C. So j omega C comes to numerator, 1 plus j omega RC is there. And the denominator also, this step is repeated, plus R plus 1 by j omega C. This is now R by 1 plus j omega RC in the numerator divided by R by 1 plus j omega CR plus R plus 1 by j omega C. So to simplify the denominator, you have to find a common denominator for this denominator term. That will be j omega C into 1 plus j omega CR. So in order that this denominator becomes 1 plus j omega CR into j omega C, this term must be multiplied by j omega C. So this becomes j omega CR. I have taken a common denominator j omega C into 1 plus j omega CR. So first term becomes j omega CR, and for this term the entire product must be there. J omega C into 1 plus j omega CR, j omega C into 1 plus j omega CR into R. Plus here j omega C is already there, then I'll have to multiply it by 1 plus j omega CR in the numerator. So the common denominator becomes this one. Now 1 plus j omega CR here and this one here vanishes. J omega C comes to numerator to make it say j omega CR divided by, you can open this bracket and club identical things. J omega CR is here, R into 1 j omega C, that make it say j omega CR. So j omega CR repeat 2 times, and here also you have j omega CR. So overall 3 j omega CR plus j omega CR into this one j omega CR, j square omega square C square R square plus 1 here. So there will be 3 different terms like this. Now we have a limitation. Clearly, the oscillation produced by the parallel resonance circuit will have an angular frequency omega equal to 1 by RC, where frequency is given by 1 by 2 pi RC, 1 by 2 pi RC, so that 2 pi F, that's equal to omega equal to 1 divided by RC. This is the frequency of the series resonance circuit also, since we have this assumption R1 equals R2 equals R and C1 equals C2 equals C. So omega equal to 1 by RC, or omega RC equal to 1. So you can substitute omega RC here, that's equal to 1. Here, that's equal to 1. Here omega square C square R square, omega RC whole square, that's also equal to 1. And J square is minus 1. So this becomes j omega CR, that is j in the numerator, divided by 3j minus 1, since j square is minus 1, plus 1. So plus 1 and minus 1 vanishes. What remains is j by 3j, that's equal to 1 by 3. So feedback fraction of this circuit is beta equal to 1 by 3. That means gain must be equal to 3, so that it will produce a sustainable oscillation as a Wien bridge oscillator. Because we require A beta equal to 1, since beta equal to 1 by 3, then A must be equal to 3, then A beta will be equal to 1. But A is given by 1 plus Rf divided by R1. That's equal to 3, means Rf by R1 equal to 2, or Rf must be equal to double of R1. This is the criteria that a Wien bridge oscillator will produce sustainable oscillation. So we require Rf to be double of R1. So what we often do is that we take a desired value of resistance R1, 1K or 2K for 2.2K standard, and here we place a port meter